Hi, welcome to one and all. Next, we will be discussing theorem, the Euler's criterion. Let P be an odd prime. Then, for all n, we have the Legendre symbol n over p is constant to n raised to p minus 1 by 2 mod p. So here we have to prove that let p be an odd prime. Then, for all n, we have n over p. The Legendre symbol n over p is constant to n raised to p minus 1 by 2 mod p. The proof is like this. If we will be proving this in three steps, three ways, or three cases. That is, one is for n divides p divides n, and p does not. If p does not divide n, then the Legendre symbol we will take three different values, and by using that we will prove this result. If n is constant to 0 mod p, that is, if p divides n, the result is trivial because since both members are congruent to 0 mod p. That is, in this case, what is Legendre symbol? If p divides n, the Legendre symbol n over p is 0, and if p in that case n raised to p minus 1 by 2 also divides, because if p divides n, then p divides this n raised to p minus 1 by 2 also. So in that case, if this divides, in both cases we can write n raised to p minus 1 by 2 is constant to 0 mod p, and also n over p is also constant to 0 mod p. So in that case, we when you combine these two, we will get n over p is constant to n raised to p minus 1 by 2 mod p. Now we take the case n over p is Legendre symbol n over p is 1. Now suppose that n over p is 1. That is, n is a quadratic residue mod p. In that case, we put it as 1. Then in that case, n is a quadratic residue mod p. Hence, we can apply the usual definition of the quadratic residues, and we can find, and there is an x such that x square is constant to n mod p. And hence, in that case, we want to find n raised to p minus 1 by 2. What is n raised to p minus 1 by 2 will be x square raised to p minus 1 by 2 from here. X square raised to p minus 1 by 2. But when you simplify this term, you will be getting x raised to p minus 1. You take 2 inside, this 2 and 2 is cancelled, so p minus 1 by 6 raised to p minus 1. That is congruent to 1, because x raised to p minus 1 is congruent to 1 because of our Fermat's-Little theorem. We have this n raised to p minus 1 is equal to 1 mod p if p does not divide n, because here also p does not divide n. So that is why here x raised to p minus 1 is equal to 1, which is same as n over p, because n over p is 1. So mod p. So in that case also, we have proved that n over p, n over p is equal to n raised to p minus 1 by 2 mod p. So this proves for n over p is equal to 1. Now just take the case of n over p is equal to minus 1. In this case, n is not a quadratic residue mod p, and in this case we consider a polynomial f of x equal to x raised to p minus 1 by 2 minus 1. F of x is equal to x raised to p minus 1 by 2 minus 1. So in this case, since f of x has degree p minus 1 by 2, the congruence f of x congruent to 0 mod p has at most p minus 1 by 2 co-solutions. So here, this f of n raised to p minus 1 by 2 minus 1 is congruent to 0 mod p has p minus 1 by 2 solutions, but this p minus 1 by 2 quadratic residues, but the are solutions. But the p minus 1 by 2 quadratic residues mod p are the solutions of this function. So the non-residues are not, because only p minus 1 by 2 solutions are there for this, because since there are only p minus 1 by 2 quadratic residues. So here this some p minus 1 by 2 residues are non-quadratic or non-residues. They are non-residues. Then in that case, n raised to p minus 1 by 2 is not congruent to 1. Why? Because already the p minus 1 by 2 quadratic are solutions. The quadratic residues mod p are solutions. So that is why. But here it is not a solution. Non-residues are not a solution, but we are assuming that they are non-residues. N over p is non-residue. So in that case we have to say that n over p, n raised to p minus 1 by 2 is not congruent to 1 mod p if n over p is minus 1, because we have assumed that n over p is minus 1. So but in the last result property, we have proved that n over n raised to p minus 1 by 2 is congruent to plus or minus 1 mod p. That is, this is either 1 or minus 1. But if in this case we have proved that it is not 1, then there is no other choice that it should be minus 1. It's not plus or minus 1. This is not 1, so that means it should be minus 1. So n raised to p minus 1 by 2 is congruent to minus 1 mod p. So here minus 1, it is minus 1 should be congruent. So this is equal to n over p. So here n raised to p minus 1 by 2 is congruent to minus 1 mod p. This, so we have proved the result for minus 1 also. Thus we have this we proved the case, all the cases. So by Euler's theorem we have n raised to p minus 1 by 2 is congruent to n over p mod p. So here by mistake there should be a congruent symbol, because minus 1 which is congruent to n over p should be there. So here one congruent symbol is missing. So I hope you have understood the theorem completely. Next we will be proving the Legendre symbol n over p is completely multiplicative function of n. To prove this, this also we prove it in two ways, because some numbers are divisible and are not. Here n over p is completely multiplicative. This is what we have to prove. For that, let us see the proof. If p divides m or p divides n, we know that p divides mn. If m and n are two integers, then p divides m and p divides anything. If p divides m or p divides n, then p divides mn. So in this way, we if what is the Legendre symbol in case p divides m? The Legendre symbol m over p should be 0, and the Legendre symbol n over p should be 0, because p divides n and p divides m, and p divides mn also. In that case also we have Legendre symbol mn over p is 0. So in all the cases it is 0. So we have seen that mn over p is equal to m over p times n over p if p divides m or p divides n. So this, for the case p divides mn, the result is proved. Now we have to take the case where p does not divide mn. If p does not divide m and p does not divide n, in that case p does not divide mn, because at least one p should divide at least one of them, then only p will divide mn. So p does not divide mn. So we have mn over p is mn over p. We have proved in the Legendre Euler's criterion that mn over p is congruent to mn raised to p minus 1 by 2. But mn raised to p minus 1 by 2 is m raised to p minus 1 by 2 times n raised to p minus 1 by 2. But m raised to p minus 1 by 2 is, by Euler's criterion, we have it is m over p mod p, and n raised to p minus 1 by 2 is congruent to n over p mod p. So when you combine this, this is m over p times n over p mod p. So from here, from this concept, we can see that this is mn over p minus m over p n over p is congruent to 0 mod p. That is written here. Mn over p minus m over p n over p is congruent to 0 mod p. So this is what we know. Now let us see what is the value of mn over p, m over p and n over p. So mn over p, n over p and m over p will take values, only values are 1 or minus 1, because p does not divide n or p does not divide m. So in that case you can take values only 1 and minus 1, because the Legendre symbol has only two values, 1 and minus 1. So that is why. So the difference can take, what are the values which this difference can take? So the difference can be either this is 1 and this is minus 1 minus 1. In that case this is 1 minus 1 0. if this is minus 1 and this is 1 and minus 1, this is plus 1, so 1 plus 1 2. And if this is 1, uh, if this is minus 1 and this is 1 and this is minus 1, this is 1 1 and this is 1 minus 1, this is 1, this is 1. In that case also this is minus 2. So in all cases this will be these are the possible values, but we know that this is divisible by p. If this is divisible by p, that means this should be congruent to 0. So since the difference is divisible by p, it must be 0. This is 0 means mn over p is congruent to m over p n over p. In this case also we have shown that mn over p is congruent to n over p n over p. Thus we have proved that the Legendre symbol n over p is completely multiplicative function of n. Now we can see a note also. Since n over p is completely multiplicative function of n, which is we have already proved that n over p is completely multiplicative. Now we prove this n over p is completely multiplicative. We have already proved that n over p is a periodic function also, and it vanishes at p of when p divides n. So n over p is completely multiplicative of n with period period p and vanishes when p divides n. It follows from a previous theorem that what is that theorem? The theorem is that there are 5k distinct Dirichlet characters modulo k, each of which is completely multiplicative and periodic with the period k. That is, we have chi mn, chi m of m, chi mn is chi m times chi n. For all mn, chi n plus k is equal to chi n. Conversely, if chi is completely multiplicative periodic mode, period with period k, and if chi n is equal to 0, if GCD of nk is greater than 1, then chi is one of the Dirichlet character mode k. So this, using this converse part, see this converse part, we can see that n GCD of Legendre symbol n over p is completely multiplicative function of n, which is periodic with the period p and vanishes when p divides n. It follows from the theorem that n over p is chi n, where chi is one of the Dirichlet character modulo p. So, and this Dirichlet character n over p, the Legendre symbol is called a quadratic character mode p. I hope you have understood this concept. Any doubts, please send your queries. Thank you very much for your patience.